this assessment points out that stabilized ylids don't react with ketones and expects us or asks us to explain why. Well, we can approach this from two reasons. One, we can say, why aldehydes and not ketones? Well, let's do that. Let's imagine this aldehyde. What is it that makes an aldehyde more reactive than a ketone? Well, that has to do with this Zwitter ion resonance structure. The aldehyde has this cation in the Zwitter ion structure only stabilized by hyperconjugation one time. Whereas in the ketone, that carbocation is stabilized by hyperconjugation 2 times. And so it makes sense that ketones are less reactive as electrophiles than aldehydes. Now, how about the ylid? Well, let's sketch the picture of a unstabilized ylid. So maybe, and we'll go ahead and draw it in this resonance form, where we have a negative charge on carbon attached. So we're drawing it as the phosphonium ion, negative charge on carbon, positive charge on phosphorus. There's nothing that can help stabilize that negative charge. Whereas for the stabilized ylid on the screen, drawing it in this resonance structure, we see that this negative charge on carbon, and again, it's that negative charge, this negative charge versus this negative charge that's making the Wittig reagent nucleophilic at all. This negative charge can be stabilized by resonance. So we can draw an additional resonance structure that stabilizes that negative charge, delocalizing it onto oxygen. And so as a nucleophile, since this lone pair is stabilized, it's less interested in reacting with an electrophile. So the fact that the stabilized ylid is more stable and the aldehyde or the ketone is less reactive, the combination of those two things is that experimentally we observe stabilized ylids don't react with ketones. Unstabilized ylids, on the other hand, are much more nucleophilic. They can easily react with ketones.